Good evening, everyone. My name is Andrew Fracknoy. I'm the Emeritus Professor of Astronomy here at Foothill College in Silicon Valley, and it's a real pleasure for me to welcome everyone here in the Smithwick Theater and everyone watching us on YouTube or listening to us on our podcast to this lecture in the 23rd Annual Silicon Valley Astronomy Lecture Series. This program and this series is sponsored by 4 organizations: the Foothill College Science, Technology, Engineering, and Math Division, the Search for Extraterrestrial Intelligence, or SETI Institute, the Venerable Astronomical Society of the Pacific, and the University of California Observatories, which includes our local Lick Observatory, and we're very grateful to them for their support. Tonight's talk has probably the best title we've had in 23 years. I love this title: Earth to Earth, Ashes to Ashes, Dust to Dust, the Birth and Death of Worlds. Wow. Our speaker is Dr. Eugene Chiang, who's Professor of Astronomy and also of Earth and Planetary Sciences at the University of California at Berkeley. He's a theoretical astrophysicist with an interest in all things planetary, from how planets first form to how they settle into their orbits, all the way to what atmospheres they come to have. He has served as the chair of the Berkeley Astronomy Department, is an elected fellow of the American Academy of Arts and Sciences, and is the recipient of the Berkeley Distinguished Teaching Award, which is the highest award you can win for teaching on the UC campus. I'm delighted to welcome back for his second time at the Silicon Valley Astronomy Lectures, Dr. Eugene Chiang.
Thanks very much, Andy. I think you can all hear me. Good. Yeah, thanks very much for the kind introduction. And let me just say what a pleasure it is and honor to give a talk for this distinguished lecture series, which has done so much to bring the universe to so many people. My talk today is on planets, both like the one we're standing on, but also worlds that are very much unlike ours. Planets both in the solar system, but also orbiting stars other than the sun, extrasolar planetary systems, or exoplanets, where the exo refers to outside of our solar system. We now know of many more worlds that are outside of our solar system, and we know, in fact, that the cosmos is just filled with them. So just to orient ourselves, we'll start with our own local neighborhood, our solar system. This video is showing really a wonderful mechanical device. It's called an orrery. It lays out what the sequence of planets is. In the middle is the sun, and it has a coterie of planets, starting with Mercury, continuing with Venus, then Earth, third rock from the sun, and then completing the sequence is Neptune, the outermost ice giant. You know that in our planetary family, there are 8 members. Of course, there used to be 9, but you know what happened to Pluto. It's best not to talk about it in polite company. This video demonstrates that an orrery, it demonstrates one of Kepler's laws, right? That planets that are closer to the star, to the sun, rotate faster. They make their turns faster than do planets on the outside. It also illustrates a principle that lies at the heart of what has been the most successful method for detecting exoplanets. And it's in this little segment of the clip, which is just coming up. Let me try to freeze the frame. So there's the Earth, right? And coming into view is this object right there. So it's a little pearl that's going around the Earth, and what do we call it? What is that? That's right. And when the moon rotates so that it's in alignment, so that it's just between the sun and the Earth, what do we here on Earth see? That's right, an eclipse. And when things are exactly aligned, we see a total solar eclipse. And I know that just last month, Andy gave a talk for this lecture series and convinced all of you to get plane tickets or somehow get to Mexico or Nova Scotia or Texas to be in one of those places on April 8th, 2024. At high noon, that is going to happen. We're going to Mazatlan, so please join us. The moon, of course, is not the only celestial object that can blot out the sun. On the right is actual footage of the sun and another body, which is crossing it. We say that it transits the face of the sun. And does anyone know what that object is? Yeah, I heard it. Good. 2012, Venus transited. And my son and I were fortunate enough to witness this event, remarkable in its own way. He was 4 years old at the time, and for about a year after the Venus transit, every time he drew the sun for school artwork, it looked like this. Yeah, and his teachers were a little worried. They asked me, is he okay? Has he been abducted by aliens? And I said, for an astronomer, there's no better Father's Day present. In this picture is actually the key to discovering planets orbiting other stars. Because if this can happen here, it can happen anywhere, and it does. So imagine a star, not the sun, but another star, having its own set of planets. Okay? Now, each of those planets is going to cast a shadow. And talk about casting a long shadow. These shadows extend across the entire galaxy. So if you here in the audience, if a shadow passes across your line of sight, what do you see? Remember, the star is so far away that you can't really make out any details, right? It's so far away that the star just looks like a pinpoint of light in the night sky. But when a planet passes in front of it, if your eyes were sensitive enough, you could tell that the star got a little dimmer. And that's the way, looking for extrasolar transits, that's the way in which that's what's the signal that there are other planets orbiting other stars. And that was the vision of Bill Barucki, a scientist at NASA Ames Research Center. NASA Ames is just down the road in Mountain View, and it was his vision to design and construct a telescope. About 1 meter in diameter was the mirror, launch it into space where it would get a crystal clear view of as many stars as possible. It stared at this patch of sky. It looks like the field of view looks like a bit of a cross. It's a 10 square degree field of view. It's between, you can look at it tonight in the night sky, it's between Cygnus the Swan and Lyra the Harp, and it just stared at this one patch of sky, 150,000 stars for as long as possible. Okay, and you don't want to break your attention, right? You don't want to get distracted because you don't want to miss it when a transit happens, when one of the stars blinks. The telescope was named Kepler after Johannes Kepler, the person in the 16th century who discovered the laws of planetary motion. For every one of those 150,000 stars, we measured a light curve. So what is a light curve? A light curve is just a plot of the brightness of the star versus time. Remember, that's the only thing you can measure, right, from this faraway star, the brightness. So what we're looking for is this telltale drop in the brightness. And of course, it'll come back up again. And it's periodic, right? It happens every time the planet orbits the star. An experiment of this scale had not been done before, so we really didn't know what to expect. Here, again, is that cross-like field of view, 150,000 points of light here, and these were the results. These colored points are the stars that blinked, where there were transits, if more than one, in fact. So the entire board lit up, and very quickly we knew that planets were everywhere, okay, in the cosmos. Here was the first one that was announced, Kepler 10. This work was led by Natalie Batalha. She's at UC Santa Cruz. And this star, Kepler 10, it's a star like our own, a little older actually. Every 20 hours, it gets a little dimmer. Okay, so here's the light curve. 1 is 100%, right? That's the normal brightness. Every 20 hours, it drops from 1 to 0.9995. Okay, so the depth of the transit, right, tells you how big the planet is. The bigger the planet, the more area, the bigger the shadow, and the more light that it's blocked out. Based on this tiny little drop, we infer that the planet is a little bit larger than the Earth. Okay, maybe 40% larger in radius than our own Earth. We call it a super-Earth. We know more than that. We also know what the period is, right? It happens every 20 hours. And remember Kepler's third law, right? It was demonstrated in the orrery that things close to the star rotate really fast compared to things that are further away. So 20-hour orbital period. Every 20 hours, it circles its sun. How long does it take us on the Earth to circle the sun? It takes, yeah, exactly, 365 days. This one completes its orbit in less than a day, so it has to be really close. So close that the surface temperature is estimated to be about 2,500 degrees Fahrenheit. Okay, so that's, for those of us who cook with ovens, broil, right, is like 475. So this is 5 times broil. So maybe not the greatest place to invest in real estate, but I think an interesting place to visit. You visited Hawaii, maybe. Lava flows. This is hot enough to melt lead. You've maybe visited Hawaii Volcanoes National Park. Hawaii is just an island in the Pacific on the planet Earth. Let me invite you to visit an entire planet called Hawaii. Okay? We can also play The Floor is Lava there, and I guarantee you, we will all lose and die. It'll be very exciting. Kepler 10 was just the earliest sign that there were many more planetary environments than we had dreamt of in our philosophy. And just to give you a sense, a more comprehensive overview of just the sheer diversity of planetary environments, let me make this plot of radius, okay, planet radius, how big the planet is, versus planet mass, how heavy it is. And right, from mass and radius, you can infer a density, right? Because density is mass divided by the volume, okay? So by putting the planets on this plot, we can get a sense of their densities. We can try to infer what they're made out of. Are they made of high-density materials, like solid iron? Or are they made of like low-density materials, like gas, hydrogen? Is it very puffy? Okay, so here's the plot, radius versus mass. All the red points are real extrasolar planets, and it's just a fraction of the ones that are known. The black points are solar system planets, and I find it really sort of gratifying that solar system planets are actually a pretty reasonable guide to organizing our thinking about the diversity of structures out there. Okay, so let's start with the solar system archetypes for planetary interiors. There are 3 types. First one is familiar to us. It's the Earth. So it represents so-called terrestrials. Okay, so Venus and Earth, Mercury are the terrestrials. And what are they? They're just balls of rock. It can be a little bit more specific. They have cores of iron surrounded by silicate shells or mantles. By silicate, I mean things like magnesium, silicon, oxygen, the elements that go into making things like sand or quartz or granite. Okay. That's the terrestrials. Second type, Neptune. So what's Neptune? Neptune is quite a bit bigger, right? It's this point right here, and it's very close twin, Uranus, 4 Earth radii, and also quite a bit more massive, maybe 15 Earth masses. So what's that type represent? It's an ice giant. So it also has a rocky metallic core, but it is so far out that ice can condense, water can condense. Other kinds of ices also exist out there. So water ice, methane ice, ammonia ice. And all of it is wrapped up in a gas atmosphere that's rather voluminous, right? A rather thick atmosphere made of the most common element, most common gas in the universe, which is hydrogen. Okay, so that's your ice giant. And finally, the king of the planets, Jupiter, the third archetype, representing the gas giants. Yes, it's made of hydrogen, but to call it a gas giant is actually a real misnomer because it's not the hydrogen is mostly not in gaseous form. The pressures inside the planet are so large. You know how you go down into a swimming pool and you feel like your head's going to implode? It's because the pressure is very high there, right? Well, try going down into the interior of Jupiter. The pressure is crazy. So large that the hydrogen will liquefy. So these gas giants are really more correctly called liquid giants. There's global oceans of liquid hydrogen in Jupiter and Saturn. So try swimming in that. Notice how these three types, this set of black points, that set of black points, and the other set of black points for Jupiter and Saturn, how the red points really nicely sew through those points. They fill in the parameter space. That's why I say, oh, they're nice guides. The exoplanets are sort of variations on our theme. So we know, right, that Kepler 10b is a supersized version of the Earth. So there's a super Earth. So this sequence right here, this family of points that I'm tracing out, this is the sequence of super Earths which grade down to Earths. But they're basically scaled versions of the same thing, balls of rock. Then there's this vertical sequence. You see that, right? And Neptune and Uranus are right in the middle. So there are things that are smaller than Neptune, and very imaginatively, the astronomers call them sub-Neptunes, like a subcompact car. But then there are also things that are larger, right? Quite a bit larger. Look, this one. This is 10 Earth radii, and it has even smaller mass. So this one we call the super puffs, okay? Because they're mostly hydrogen, very airy, like your puffer down jacket. It's just really airy. And finally, you see all these points up here, right? They're sort of inflated versions of Jupiter or supermassive versions of them. And so there are the super Jupiter types. So this is just to give you a flavor of what's out there, of what we've learned. Here's another illustration of the diversity of exoplanets. And it's about the orbital diversity. This is the 21st century digitized version of an orrery, right? Not of our solar system, but of all the other solar systems that people have discovered. And again, this is just a fraction of what's been discovered. This nice compilation this animation was created by my colleague at the University of Chicago, Dan Fabrici. And every one of these points, right, these circles, corresponds to a planet, and the size of the circle scales with the size of the planet. So there are things like from sub-Neptunes all the way to super Jupiters. Time elapses according to this counter here, and it's in days. Okay, so I could stare at this all day. There's a lot going on, right? All these clocks running in the universe. Here's one of my favorites. See this one? Yeah, it's like a mosh pit of super Jupiters. These just giant planets that are so close to their host star that they're just running around on like sub-day periods. Okay. This concludes, I think, sort of the first segment of my talk. I've tried to give you a taste of what's out there today. right? So the present day universe, what planetary systems look like now. I'm going to shift gears now and travel back in time to ask the question, how did all this appear? Like, where did this come from, right? So questions of origin. You may have heard the term cosmology, right? The study of the origin of the universe. I'm going to address a related question, the question of cosmogony, which is the study of the origin of the world, or in this case, worlds. Before I do that, I thought it worthwhile to just sort of highlight how the study of origins is a very deeply human impulse. I had a philosophical moment when I was preparing for this talk. And why are we so interested in origins? Why are biographies, at least well-written biographies, so compelling to read? It's because we want to know, right, how Jennifer Doudna became the great scientist that she is. On a more fanciful note, superhero movies, right? I think we can maybe agree that there's a glut of them. For my money, the most interesting ones are the first in this series, like the origin stories, right? The sequels, yeah, there's just a lot of fighting. But the origin stories are compelling to me. They discover their powers, and they're struggling with sort of issues of identity. I'd like to know how they became the heroes that they are. And the study of origins even extends to my dog, because the number one most popular question asked of my stray is, what breed is he? Where did he come from? What is his lineage? And the thing with origin stories, right, is that there's often more myth than fact. And for very good reason, because the evidence that we have is often fragmentary. It's hard to be conclusive about origin because we weren't there. And planet formation is no exception to that, okay? So I'll try to stick to some robust ideas about planet formation, also include some recent developments, but there's a lot out there. I would have to say that's myth. Okay, I'll try to avoid that. To understand the origin of planets, we need to take a step back, almost literally, and zoom out to look at the bigger picture, the picture of the galaxy in which we live. So here we are, a small, unregarded yellow sun in a collection of hundreds of billions of stars making up our Milky Way. What is the Milky Way? It is this collection of stars that's arranged in a disk, like a pancake, and it's swirling around. And you can tell which way it's swirling because the arms are trailing, so this entire disk is rotating clockwise, I believe. Okay, now here we are, out there in the boonies, some 24,000 light years away from galactic center, just to give you a sense of scale. You know what a light year is? It's the distance that light travels in a year. And light, being the fastest object in the universe, a light year is a pretty long distance. There are many ways to try to wrap your head around this distance. My way is to convert my frequent flyer miles into light years. Okay, so in my 50 years of flying, I have accumulated all of 1 light second. Which, when I put it into galactic context, I don't feel so bad anymore that I still don't have premier access. So that's just to give you a sense of how big the galaxy is. And this is just our galaxy, not to mention the other galaxies in the observable universe. Okay, this image, right? I used to see it on T-shirts all the time, like, we are here, okay, so don't panic, like, don't get lost, you're here. It's a bit of a cheat because this is not actually a picture of our galaxy, right? Because in order to take this kind of picture, you'd have to be above the pancake, right? And we just haven't nowhere near traveled that far. So we're in the pancake, right? So what does the galaxy look like to us? Well, this is what it really looks like. This is what it really looks like, okay? The Milky Way. And it's this beautiful band of light that arcs across the sky, okay? Because we're in the pancake. This is what the pancake looks like when you're in it. And what's interesting from a planet formation point of view is not so much where all the light is from all the stars, it's where the light isn't. So these dark splotches, why are they so dark? They're clouds, I mean galactic scale clouds, okay? Hundreds of light years across. And they're filled with dust. And the dust obscures the starlight, and so you don't see as many stars. That's why they're dark. It's like being in a sandstorm or in a smoke-filled room. I mean, you sort of can't even see the hand in front of you. It's so dusty. We actually have samples of these dust grains. I find that remarkable. Not that we actually went out there and like picked them up and brought them back. They came to us. They were preserved in meteorites which fell to the ground, okay, for us to look at. It's just remarkable to me. So here are some actual images of, I mean, these are real dust grains it came from outer space. Notice the scale here. The grains are tiny. This is micron scale. So what is a micron? It's 1/10,000th of a centimeter. And what are the grains made out of? They're made of things like silicon carbide, this is a graphite, so it's a carbon grain. This is a metallic mineral, spinel, silicates. They're made of the same things that the Earth is made out of. So, and the cores of other planets are made out of, right? The rocky metallic cores of planets. So the story of planet formation really begins here, with tiny, literally microscopic grains of dust that somehow congealed to form these massive structures that we live on. I say the story of planet formation starts here, but a more fundamental statement, okay, is that the story of star formation starts here in these clouds. Because these clouds contain not only dust, but also gas. They contain the most common element, the most common gas in the universe, which is hydrogen, which is what the sun is made out of. So stars form from these clouds, and by extension, right, planets form around those stars. Planet formation, you should really think of as a byproduct of star formation. And I'm going to get into that in greater detail right now. Let's zoom in on one of these clouds. This is what the Hubble Space Telescope sees when it zooms in on one of these clouds. It's brighter than you think. All of this gas, it's hydrogen, trace amounts of oxygen, nitrogen, it's all lit up, right? These colors, by the way, the blues and the greens, they're very similar to the northern lights or the southern lights if you've ever seen them. It's all lit up by the young stars that are born. These are all young stars that freshly minted from the cloud. Okay, here's a cluster of them right here. Okay, and so that's what lights up the cloud. Notice these little dark nuggets. I mean, it's really dusty in there. I hope you get a sense from an image like this that the entire cloud is just in constant roiling motion. It's highly turbulent. Here's a physics-based animation of that motion. They're like whitecaps on the surface of a choppy sea, except it's even more complicated because it's in 3D, yeah? And all of this activity, all of this turbulence is driven by gravity. So you have, some clump of gas over here, it gravitationally attracts another clump, these filaments collide, and they make the gas denser at the interface, at the shock interface. Where it's denser, the gravity is even stronger, and where gravity is even stronger, you have a fighting chance of forming a star, right? Because gravity wants to collect all this material into a smaller and smaller volume, and then it lights up to become a star. We can zoom in on one of these nodules, right? These sort of nuggets, these dense nuggets inside the cloud. Here's a zoom in, and notice the scale here. The previous scale was something like 100 light years across. This is now a fraction of that. This is maybe half a light year across. Okay, so this is one of these dark nuggets. The total mass in here is about a solar mass. That is about as much mass as is in the sun. This cloud, which is filled with hydrogen and dust, because you can't see through it, it's definitely dusty, this cloud one day will become a star like the sun, or maybe two. Okay, maybe it'll form a binary. We know this because we can detect, we can measure how the gas is moving. One component of that motion is inwards. Makes total sense, right? Because that's what gravity is trying to do. It's trying to pull all the pieces of the cloud into a smaller and smaller volume. Now, it's got a long way to go before it forms a star, okay, which I've just drawn in. This is just a little cartoon. It's got a long way to go. It has to shrink by a factor of 10 million before it gets to the scale of the sun. It's got a long way to go. But, you know, we're patient. If you have 100,000 years or a million years, it can do it. Now, situation is just a little bit more complicated than this, right? Because this is just one component of the velocity. And by the way, we can measure these velocities by using Doppler shifts. The other component of the velocity is all of this roiling motion. Don't forget, the cloud is turbulent. Okay, so there's all this churning and, you know, topsy-turvy movement, and I'm going to represent this random component of the motion with a little swirl. It's like, you know, it's like an eddy in a turbulent medium. It's like the spin velocity of the eddy. We can think of it as a spin to the entire cloud. Okay, so now the question is, you have this cloud, it's trying to shrink under gravity. At the same time, it is spinning. And the question is, what happens, and this is now an artist's impression from a textbook, you have this, you know, it's the same scenario that I've been talking about. You have this infall, but at the same time you have this spin. The question is, as the cloud is contracting under gravity, it's spinning at the same time, what happens to the spin as it contracts? Does it spin faster or does it spin slower? Yes, well, let's test that. So this figure skater will set herself into a slow spin. Okay, she'll arc around, and then she will simulate gravity by pulling in her arms, and for sure, the contraction leads to a faster spin. Now, spinning faster, is that good news for star formation or bad news? That is, if you're spinning really fast, does it become harder or easier for you to keep contracting? Remember, you've got to shrink by a factor of 10 million. Now you're spinning like mad. Is it easier for you to complete that contraction to form a star, or harder? Yeah, well, let's test it. Let's ask the pizza guy. So here's a piece of dough. Okay, notice how big it is. It's about the size of his hand, and he's going to very expertly toss it. He's going to set it into spinning motion, faster and faster and faster, and it's getting bigger. It's really big now, right? So yes, it gets harder to contract because of all the centrifugal forces which are flinging that material out. Okay, so this is why not all of the material, right, from that original cloud, that dark cloud, can shrink to a point. Some of it is spinning so fast that it's stranded in this disk. Okay, it's leftover material which just can't go all the way because it's spinning too fast. That may seem like bad news. It's good news for us, because the planets form from this leftover spinning disk, right? We literally owe our existence to the centrifugal force. It's this leftover material that ultimately congeals to form planets. Is it any wonder then, right, that in the solar system, all the planets, like they're spinning around the sun, and they're like in this nice pizza sheet. This looks just too good. I'm quite hungry, actually. So I think I'll take that to go, maybe with some super Earth toppings. And if you can add an extra sprinkling of asteroids, that would be great. Now, this conception of a circumstellar disk we sometimes call them protoplanetary disks because we hope that they really will form planets. These were just ideas for, I think, literally centuries, back to the time of Laplace, okay, like the 18th century. It was only in the 1990s, that we finally saw evidence for these disks. And one line of evidence was from Hubble again, and see, here they are. If you zoom in on some of these dark spots, or these stars rather, wow, there's these disks, okay, orbiting these stars. And they're in silhouette, they're dark, because they're just full of dust. So they block out the light from the background nebula. We've been able to zoom in even further, okay, very recently with the Atacama Large Millimeter Array, and to make images like this. And this, I should say, this is an actual object. This is the artist impression, and this is actual data. And I'll tell you, when I first saw this image come out, I thought, oh, there must be some prank. It must be some, fancy AI Photoshop. But no, this is actually what the radio telescope sees. And I should point out that all of this emission, it looks red, it's just bright, because it's coming from dust again, but dust now in emission, okay? Because you're looking at longer wavelengths. The dust is warm enough that it can radiate, emit radio waves for us to observe. Technically, actually, microwaves, the same kind of radiation that comes out of your microwave oven. Yeah, these dust grains, they're warm enough that they can radiate microwave radiation for us to detect here on Earth. And the resolution is just incredible. So these are other disks, okay? And all of this structure, and it is so tempting to say, yes, there is a planet here. It's inside the dark lane. It's just orbiting around. It's consumed all of that material in the disk, and it's clearing it out. And now, where the field is now, is to search, is to find, and actually confirm the existence of these protoplanets, these youngest of planets that we believe, but have not quite yet confirmed, exist inside these dark lanes. Okay, and it may be a job for the James Webb Space Telescope, which very recently successfully launched. Okay, that's all I'll say about origin. For the last part of my talk, I'm going to now shift the gears again for a final time and go forward in time and try to project the futures of planetary systems. Where are we headed? Our fate as a planet orbiting the sun is tied to the fate of the sun. The fate of the sun is to eventually run out of gas. You know that the sun and stars like it are powered by fusion, nuclear power. It's very safe. It's the burning of hydrogen into helium. And that conversion of hydrogen into helium produces light and heat, powers the sun. Eventually, you're going to run out of hydrogen in the core. At that moment, the pressure in the core is going to drop, right? Because you've lost your power source. When the pressure drops, gravity says, okay, time to start shrinking again. And so that material is going to start collapsing in on itself. But when it starts collapsing in on itself, it compresses, right? And you know what happens when you compress gas. You're doing work on it, it gets hotter again. So now you have a chance at a new lease on life. It gets hotter again, hot enough, just a little bit, hot enough that it triggers a new set of nuclear reactions. Still burning hydrogen, just sort of the leftover hydrogen that's in the vicinity. It's hot enough that you can burn that residual hydrogen that's around. Now, here's the catch, okay? Here's the fine print on this second lease on life. The fine print is that nuclear reactions are extremely sensitive to temperature. So a tiny increase, a modest increase in the temperature in these stellar cores means that the nuclear reaction rates burn a lot faster. You produce a ton of power this way. You produce way more power in this emergency generator plan, this, plan B. You generate more power than what you need. I always find this sort of ironic, tragic. I think there's a parable in here somewhere. It's like you're running out of gas, right? You're running out of gas, you're running out of gas. And what do? You're just going to take whatever gas you have left and burn it even faster. So the star does not conserve it. It just says, okay, I'm going to really go into high gear now. Okay, so that's what it does. That's what it's going to do 5 billion years from now. And the consequences for us are devastating. So here's the artist impression. Star's going to get more luminous, bigger, brighter. The first planet to go is going to be Mercury. So long. Next one is Venus. We're third in line. Before we say goodbye, it's going to get really, really, really hot. I don't do very well in hot weather, so I'm really not looking forward to this. There's a poem, from Robert Frost called Fire and Ice. So you know how it goes, right? Some say the world will end in fire. Some say ice. And I say, just ask an astronomer. We know how it ends. It ends in fire. Okay, and there are some reactions to this on the internet, often amusing. So Busy Buddy says, 5 billion years from now, let's all get into the sunscreen business. Yes. Pietro Porto says, the preview is looking good. Can't wait to see it live. I'll tell you, I can wait. I don't need to see this live. But I'll tell you, if you do want to see it live, you can see it live. Not here, but elsewhere, in extrasolar systems, some of which are undergoing this fate right now. You want to see one? Okay, so this was one of the surprises of the Kepler from the Kepler survey, that one of the 150,000 stars was doing this. And here it is. It's this object. Here's its light curve. Looks kind of complicated. I'll walk you through it. Let's just look at this panel over here. A light curve, right? The brightness of the star versus time. This is measured in days, so this is about 10 days across. And like clockwork, there is a transit, right? Every 685 hours, there is a transit. Oh, there's a dropout. Oh, there's a dropout. Okay, that's like clockwork. This is very short, so you know that it's pretty close to its host star. Okay, so close that the surface temperature is over 3,000 degrees Fahrenheit. Now, what's not like clockwork is the transit depth. You see that? It's a little hard for me to see from this perspective, but let's look at one of these deep ones, like this one, I think. So that, right, the brightness dropped from 1 to something like 0.99. Now, a 1% drop may not seem like very much to you. Among my colleagues, this is enormous. A 1% drop corresponds to basically a gas giant, right, the size of Jupiter, crossing the face of this star, like this big bloated thing crossing across, okay? So you say, great, I found a Jupiter. Well, have you? Because less than a day later, 16 hours later, the next transit, it decides, by the way, I'm not that big. I'm actually only half as big. So what happened? Like, what happened to you? This incredible shrinking planet? And this is just a single orbit. This is less than a day. It went from this to that. And then it did something else, and something else, and something else. So this is like the schizophrenic planet. It's like this. Nobody had seen anything like this before. Okay, and here it is. Here's a longer time stream, okay? You can see it's just completely erratic. It's so weird that sometimes it performs a magic trick. It says, goodbye. For a while, it doesn't even show any transits. It goes poof, magic trick, vanishing act. And it's not even there anymore until it's back again. And say, oh, fooled you, I'm back. I'm as big as Super Jupiter now, until I'm not. Completely random, okay? It's even weirder. So if you take a look at the transit, the shape, of the transit. Remember the Kepler 10b, this nice square well, like it comes in and then it goes out, everything's nice and orderly. This is not quite like that. It's not symmetric. It's fast going in and it's slower going out. It doesn't even have a flat bottom. It's fast going in, and then it sort of drags its feet to come back to normal brightness again. So this is one of these classic, elephant moments in science, right? Because like the three scientists, they're blind, and they say, oh, I think I see a trunk, I feel a trunk, and I think there's like a tail, and then somebody hears, oh, it goes like, arr, and what is it? And these are the questions that we had. Saul Rappaport and Al Levine of MIT had discovered this object, and we all got to thinking, what could it possibly be? Okay, well, this is what we think it is. We think it is a planet, okay, a planet that's dying, and that in its final death throes, it's disintegrating under the glare of its star. It's so close. As it's disintegrating, it is acting like a comet. You know what a comet is, right? It's one of these balls of ice, maybe a kilometer in size, gets so close to the sun that the ice evaporates, creates a tail. Okay, so take that picture and modify it to make this. So you take a kilometer-sized ice ball, first make it 1,000 kilometers, okay? So it's like planetary scale. Take away all the ice, because it's definitely all gone at this temperature. Replace it with rock and metal. Now put it even closer to the star, hot enough to vaporize the rock and the metal, to create this tail of dust made of rock and metal. And that's what you're looking at. So what we think is going on is something like this at the surface, something like this in the NASA animation. Okay, there's the comet. I can't quite see it from this angle, but I think you can. There's the comet, right? But it's a mega comet, okay? And comets, are notoriously time variable, right? If you've ever tried to look for a comet, it's this fuzzy thing, and one night it'll have, this beautiful tail, and then the next night it'll be like, isn't this kind of sort of lost a little bit of steam? There are fissures, there are geysers, there are jets coming off, and it's all rather random. So, sometimes the tail is very thick, and sometimes it's a little thin. The tail works great to explain the asymmetry in the light curve, right? Because it's dragging its tail across the face of the star, which is why it takes so long for it to egress, to exit the transit. Why is it so variable? So literally, when I look at this system, it's literally throwing its ashes into the wind, quite literally, into the stellar wind, no less. Okay, this is how the planet is dying. It does not go gentle into that good night. It fits and starts, and really a violent death. We've been trying to understand more of this randomness. It's basically like the weather, which is also irregular and chaotic to a large degree. And rather than go into all this, let me just say that the system, right, it alternates, we think, between these two extreme scenarios. On the one hand, the skies can be so clear, the surface can be so hot that a wind is launched, right? This vaporized rock and metal is launched from the surface of the wind, a very strong jet, right? And it's sort of like a runaway greenhouse solution. It's really hot. But at the same time, there's another extreme that it also bounces to, and that's a nuclear winter scenario. That's when the jet is so strong, right, that it obscures the light from the star, and the surface of the planet gets darkened to the point where it's cold enough now to stop vaporizing. So it really is schizophrenic. It doesn't know, right, what it wants to be. It chaotically bounces back and forth between a runaway greenhouse solution and a nuclear winter scenario. So you don't have to pick your poison. You get two types of apocalypse for the price of one. Eventually, the planet will be swallowed by the star, and we've even seen this, not for that planet, okay, but for another one. And this was recently announced. It was just announced last month. And when it's finally swallowed, there will be a last hurrah. There's going to be a flash. And people think that they've seen this flash around this red giant, the red giant star, this bloated, old star, increased its brightness versus time, and it got brighter by a factor of 100. And then over the course of a year, it went back down again. This flash is thought to be the final collision, the final merger between the planet and its parent red giant. Okay, and then you can ask the last question, which is what happens next, right? The red giant, after having consumed all of its planets, what happens to the star eventually? Well, it gets even brighter and bigger and brighter and bigger and bigger and then fainter until it finally dissolves into interstellar space. And that's what it does. And you might think, oh, I guess the story's over then, right? Well, no, the story is actually just starting all over again. Because all of that material from the star and all of the consumed planets and all of the ash, it's literally been scattered back into the galaxy to form a new cloud, which can then cool and contract under gravity and form a new generation of stars, and by extension, a new generation of planets. So it really is, it literally is this renewable life cycle that we're all a part of. Dust we are, and to dust we shall return. That statement is true in every sense of the word, in every sense. And it's a cycle that we're all literally a part of. So I hope you found this interesting, and I guess I'll take some questions. Thank you. Yeah.
My question has to do with volcanoes. I haven't heard you mention that, but I kind of wonder if you can see volcanoes in the same way that you can see some of these dust storms in some of these planets.
Not around extrasolar planets. The emission from the planets is generally too faint for us to see. People do see emission from the planets, from the secondary eclipse, but there just hasn't been enough data to really look for time variability. That would be, I think, the signal, right, for a volcano, when it suddenly got brighter in the infrared. You need a long enough time baseline to see it. So in principle, yes, possible, but we just don't have enough data yet to really map out the light curve of the planet itself. You may already know that there are volcanoes other than on the Earth, right? Io, of course, is the most famous one. So yeah, volcanoes exist on other worlds in the solar system, on the moon of Jupiter, Io. But for extrasolar systems, yes, you can look for them from time variability. It's just that it hasn't been achieved yet.
I also like that picture, the first part where you have planets rotating. Can you explain how that table was compiled? Because Kepler's law, there is a square and a cube.
Yes.
And in the table you have more than 2 dimensions, right, of variables. By
the table, what do you mean, the table?
I forgot the word. It's not table, it's that rotating things.
Oh, you mean the orrery?
Correct, yeah. How did you compile that? So I just want to ask, what's the parameters in that?
Yeah. Okay.
Orrery?
So the orrery, I think, is actually a simplification of what's actually going on, right? My understanding is that the orrery doesn't actually. Most orreries, maybe there are exceptions, but most orreries, I think, are circular. Okay. So that already is an oversimplification. Kepler's laws, depends on which law you're interested in, but generally speaking, we move on ellipses, right? So already the orrery has lost that feature of the motion. Now, Kepler's third law might still be captured by the orrery, right? P squared goes as a cubed, right? The square of the period scales as the cube of the semi-major axis. That, I think, that can be embedded in the orrery. And that's a matter of getting the gear ratios right. Your question, I think, was also how did Kepler come to this
no.
realization.
My question was the table, so like not orrery.
Ori, yeah.
So I would, I just want to see which parameters were captured there, because I was looking, it looks nice, but I couldn't understand where to look at.
Yeah, my guess is that it captures maybe just to order of magnitude Kepler's third law, which is, period squared goes as semi-major axis cubed. I think it gets the relative periods right.
Right.
Okay.
Some of them are bigger and smaller, and I got confused because size or mass of the planet is not in the Kepler's law. So, and those planets bigger and smaller, and I look at them and I so much puzzled I didn't understand.
The planets themselves, the spheres themselves, those are totally out of proportion.
Ah, right.
Yeah.
Okay. Thanks.
Yeah.
Hi, I would like to know how you tell a star has multiple planets. Is it by the orbits themselves and the length?
Yeah, great question. So you see a dip, right? Every orbit, let's take one planet. It'll have a very strict period, right? Let's say 10 days. You'll see a dip. But in that same star, quite frequently, you'll see another set of dips having a different period. So maybe the other period would be every 30 days. And it doesn't have to come to the same depth, right? So it's just an independent, you see, set of transits. So there's a signal at 10 days, and then there's another set at 30 days, and maybe another set at 100 days, and there you see it, right? It's just these superposed transits from multiple planets. Does that make sense?
Yes, it does.
Yeah.
Were these determined or detected via a computer program, or was it?
It's all from the data.
It's all from the data?
It's all from the light curve,
Okay.
right? And sometimes you just pick them out by eye. You look at the light curve and say, oh, there's a dip. Oh, and there it is again, and there it is again. But then you say, oh, what's that dip over there? Does it have a counterpart? Oh, yeah, it does have a counterpart over here. So you can almost pick them out by eye from the light curve.
Thank you.
Yeah.
Why aren't there any or many very massive rocky planets?
Oh, that's a great question. That is a great question. That gets into like formation theory question. There could be, in principle, there's nothing against the laws of nature, I would say. You ask a great question. I think there's no physical law, right, that would prevent the formation of, say, I don't know, a 300 Earth mass rocky body. And you're absolutely right. Those things have not been discovered yet. Okay. And there's no physical law that prevents it. Planet formation theory, and this is now getting a little bit more speculative, okay, says that once a planet's core becomes, say, 10 or 20 or 30 Earth masses, then it can start accreting gas, hydrogen, okay, which is a lot more abundant than rocks. Most of the mass in the universe is hydrogen, so there's a lot more hydrogen out there than there is in silicates. But once that core grows to maybe 10 or 20 or 30 Earth masses, it can accrete the gas a lot more efficiently. And so before you reach 300 Earth masses worth of rock, you accrete all this hydrogen and you become a gas giant. Yeah, and that theory, I've worked on it a little bit. I think it works, but I hope that's some answer to your question, is that they become gas giants before they become rock giants. Yeah.
So if I remember correctly, the first stars would have been hydrogen, and then that would have allowed more complex elements as they live their lifestyle or live their life cycle. So my question is, our own sun, what generation would that be?
I thought somebody would ask this. Yeah, I was thinking about it the other day. I think it's a little bit hard to ask because the sun is made of elements. It's a great question. the sun, so I haven't looked into this in great detail, but the sun is made up of all these metals, right? And which, as you recognize, came from other stars that have died, right? And exploded and shed their remains into the galaxy as a whole. So when you ask what generation, well, a lot of the metals, I think, came from massive stars, right? Stars more massive than the sun, having shorter lives, right? And so it's not just the sun begets a sun begets a sun. It's that the sun is made up of multiple generations of multiple kinds of stars in the galaxy. So the massive stars, right, that we inherited our metals from, our silicon and oxygen from, and iron from, I should say, they may have been like many generations, like definitely more than one, if not like maybe 10 or even 100 generations of stars. Okay, because those more massive stars, they have very short lives, so their cycles are very fast. So I would say our sun is composed of material from, say, the 100th generation of a massive star. I think that's fair to say.
Hi, thank you for your talk. It's really wonderful. And I really appreciate the idea of life circle of planetary nebula or planetary galaxies. And it really inspired me of what Carl Sagan have said, that the cosmos is within us. We are made of stuff, right? Star dust. And we are way the universe to know itself. And my question is this: if there is a life circle of universe, or to call it, if there's a thing before the Big Bang, or if there's a thing after the heat death, if there's a snap finger says, oh, it's too dark here, like, why there's no light? Let's just get some light. And that's my question. If there's a life circle of universe, or what's after the heat death?
Yeah, no, that's I think a little bit above my pay grade. That goes into like multiverse theory and the origin of the universe in the first place. Yeah, there are theories out there that, that our universe is just sort of a recycled version of itself. Although I will say the current data, my understanding is that the universe is going to expand forever, right? We know this now, having measured the energy content of the universe and the energy density. So there used to be an idea that maybe there was so much gravitational attractive energy that the universe is expanding now, right? But that there's just so much stuff in it that we would halt the expansion and then come back again and then bounce like that, right? That used to be a theory. I think it still is, but for our universe, we don't have enough of that matter to bring us back again, to halt the expansion. So as far as we can tell, we're just going to keep coasting and coasting and coasting forever, the universe as a whole. So yeah, just one generation. Yeah.
So when the sun goes from what we know now to its red giant phase where we get swallowed, what kind of time frame do we think that would be?
Roughly 5 billion years from now.
Well, when it starts, but when it gets to the red giant, out to our orbit, how long does it take that next phase to?
Oh, it's much shorter. It's much shorter than that. I forget my stellar structure, but it's much shorter. It's much shorter. So yeah. When it goes, it's going to go.
All right. Well, thank you very much. In 5 billion years, we have time to learn a lot more astronomy. So this series will continue next year, starting in October. And we invite you to come back. Keep your eye out for announcements of the lectures. And in the meantime, we want to thank Dr. Chiang again for a wonderful talk with a lot of great analogies. And let me wish all of you a good summer, and we'll see you in the fall.